Okay, we are continuing our discussion of basic hydraulics and wrapping it up with dynamic pressure. There are several factors to consider when you're determining dynamic pressure in an irrigation system, including pressure at the water source, any changes in elevation, which are going to really work the same way as they do with static pressure, and then friction loss in the irrigation system, whether that be through pipes or other components. So the calculation is going to involve the combination of all of those things. Pressure at water source, which for our purposes and for the purposes of the assignment are going to be given to you. Pressure changes due to elevation, which you'll calculate. Pressure losses due to friction losses in the pipe, which we went over quite a bit in the friction loss lecture. Pressure losses in other irrigation components like valves, the meter. This can also include pressure loss in the any backflow prevention device or filters, things like that. And then pressure losses due to fittings. So fittings are what are the irrigation components that allow you to join the different pieces of pipe together in an irrigation system. So T's, elbows, things like that. So here's an example in which we have some information. I will give you some information as well. The information we have is that this is a 100-foot length of 2-inch Schedule 40 PVC connecting the water meter to the valve. And we can see here the valve is 20 feet lower in elevation than the meter. The flow rate is 50 gallons per minute, and the pressure we have coming from the meter here, it's 60 psi. So the question is, what would the dynamic pressure be at the valve? First, you've got to consider what's happening with elevation. So we know there's a 20-foot change in elevation from the meter to the valve. So you would simply multiply that 20 times our constant of 0.433 psi per foot for a change of 8.66 psi. The next part of the calculation is determining friction loss in the pipe. So we're working with 2-inch Schedule 40 PVC, and let's go over how you use that chart one more time. So here is the appropriate chart. We know we're working with 2-inch nominal size pipe and a flow rate of 50 gallons per minute. So let me just blow up the relevant portion of the chart here. So this row is for 50 gallons per minute. This column is for 2-inch nominal pipe size, and we see that the friction loss is 1.83 psi per 100 feet of pipe. So now calculating the pressure at the valve, you combine all of that information. You've got the pressure coming into the system at 60 psi. You have the additional pressure of the elevation change, 8.66 psi, which in this case is positive because we're going downhill here. And then you subtract 1.83 psi, which comes from the friction loss we determined with the chart for this pipe, ending up with pressure at the valve of 66.83 psi. So let's look at an example where the elevation is working the opposite way. Here we're working with Class 200 PVC 2-inch diameter pipe. The valve in this case is 50 feet higher than the water meter, and the pipe length is 200 feet. We also note there's a flow of 50 gallons per minute. So first, beginning with elevation, the pressure decrease due to elevation is 50 feet times our constant of 0.433 psi per foot, and that equals 21.65 psi. The friction loss from the chart is 3.02 psi. Let's go over how you're going to get that number. So you begin with the correct chart, Class 200 PVC, and I'll blow up the relevant portion again. And you consider the flow rate, which was 50 GPM along this row, the pipe size, which was 2-inch nominal along this column, and you end up with a pressure loss of 1.51 psi. But we also had information given that this was a 200-foot length of pipe. So you take that 1.51 psi per 100 feet and you multiply it, ending up with a psi loss of 3.02 psi due to friction in the pipe. So putting that all together, you have 60 psi coming through the meter. You subtract the 21.65 psi loss due to change in elevation. You also subtract the psi loss due to friction in the pipe, ending up with 35.33 psi for this particular example. Now in this case, what you see is a situation where the water is coming from a water tank. The valve is open, that's how we're determining dynamic pressure, and the sprinklers are operating with a total flow of 30 gallons per minute. All the pipe between the tank and the valve is 1.5 inch Schedule 40 PVC, so what would the dynamic pressure be at the valve? We're going to ignore the tank and any fittings for this particular example, just for now. So here's the chart for Schedule 40 PVC again, and remember this time we're working with 1.5 inch pipe at a flow rate of 30 gallons per minute. If I blow up the relevant portion of the chart, I would be coming across here at 30 gallons per minute, coming down here 1.5 inch pipe, and I see that the pressure loss is 2.42 psi per 100 feet of pipe. So going back to our calculation, the pressure at the valve is going to equal the pressure increase due to elevation minus the friction loss. So the increase due to elevation was 120 feet plus 40 feet. Let me just go back for a second and show you that again. So you had 120 feet here. You had an additional 40 feet here. That's where that elevation change is coming from. Times our constant of 0.433, we end up with a pressure of 69.28 psi. The friction loss in the pipe, we looked at the chart, is going to be 2.42 psi times 280 feet of pipe. When you work that out, you end up with a friction loss of 6.78 psi. So putting it all together, the pressure at the valve is going to equal 69.28 psi minus 6.78 psi, and that leaves you with a pressure of 62.5 psi at the valve. But there are, of course, other losses, friction losses going on in the system. Pipe fittings, which I mentioned at the very beginning, you can determine what those losses are exactly if you go to tables similar to what I've shown you with pipe friction charts. There are such tables and charts for pipe fittings, but in design, what's typically done is there's just a rule of thumb used. So that rule of thumb is that there will be a 10 to 20% loss of pressure due to the fittings, and that's a 10 to 20% loss of what you're calculating with friction loss in the pipe. So I'll go through that and hopefully that'll be clear. And then of course the other components as well. So the way you find out what friction losses are for those other components is to go through manufacturer catalogs or specifications that might accompany those other components. So valves will have information about how much friction loss you can expect. Same with backflow devices, filters, and so on. And your textbook even has some general charts that address the amount of friction loss you're going to see in those particular components. So here, what I want to show you are some typical pressures and flow ranges for several categories of sprinklers and drip emitters. And it's good for you to have a general idea of the pressure and flow ranges for different sprinklers so that when you're using an irrigation system or perhaps troubleshooting an irrigation system, you can tell if the pressure is not appropriate or correct for that particular situation. If the dynamic pressure is significantly higher or lower than what you see here, it may indicate that there's a problem that needs to be investigated. So here what you've got are different sprinkler types, different emitter types, the ranges of pressure which they operate under, and I want you to just carefully note that the pressure ranges for drip tend to be significantly lower than the pressure ranges for spray or overhead type emitters, and also note that the flow ranges for spray or overhead type sprinklers tend to be designated in gallons per minute, and drip tends to be designated in gallons per hour. So higher flow, higher pressure, lower pressure. So just having a general sense of those is going to help you to know if things are basically okay in terms of pressure or whether that needs to be looked at more carefully. So let's go on with another example. Here we're trying to figure out what the dynamic pressure is at this last sprinkler on the lateral line. The information given includes the pipe sizes in between the sprinklers, so that's what these numbers are here. So 3/4 inch, 1 inch, 1 1/4 inch, 1 1/4 inch. And this, by the way, is typical where you will have different pipe sizes along a single lateral. So you would need to do separate calculations to determine the friction losses along those different sizes and sections of pipe. All right, we also have other information. We know that the pressure at the valve is 60 psi, and though it's not listed here, the distance in between each pipe I'm going to give you is 46 feet. So how do you go about determining the dynamic pressure at this last sprinkler? This is how I would recommend arranging your calculations, and you will have questions like this in both the assignment as well as exams coming up. So just do it this way. It's very straightforward. It allows me to see that you have considered things in a logical way. So here on the left you've got each pipe section labeled A through D. The type of pipe is noted, and this can be different, so you want to make sure you note that. The size of the pipe is noted here. The gallons per minute required, and this relates to the flow through each of the sprinklers. The length of the pipe, and then the PSI loss per 100 feet. This comes from a chart. And finally, the actual PSI loss. So let's go through exactly how you would do that. I'll talk through the calculations, but as the calculations have already been done here, the total PSI loss through the pipe is 3.42 PSI. So if that were considered along with what's happening at the valve, you have 60 PSI. You've lost 3.42 PSI because of friction in the pipe. Here we're bringing in the pressure loss in the fittings now, using 10% as a rule of thumb. So 10% times 3.42 is 0.34 PSI. Putting all of that together, the pressure remaining at that last irrigation head would be 60 PSI minus 3.42 PSI, which is the loss here due to friction in the pipe, minus 0.34 PSI, which we determined up here as the pressure loss through the fittings, and we end up with a dynamic pressure at the last sprinkler head of 56.24 psi. Now again, I just want to go through and review how the chart would be used. Let's just look at one section of the pipe. If you recall, section A, the pipe was 3/4 inch class 200 PVC, and the flow was 6 gallons per minute. So the PSI loss, using the chart here, we have the 3/4 inch column, we have the 6 gallon per minute flow rate, and the pressure loss is 1.86 PSI per 100 feet, and that's what you see here on the table. But recall the length of pipe in section A, well, all the sections, but we're working on section A right now, was 46 feet, not 100 feet. So you would take that 1.86 PSI loss, divide it by 100, you end up with 0.019 PSI loss per foot of pipe. So the actual PSI loss in that section would be 0.019 PSI loss times 46, or 0.086. So let me just go back here. That's where this number is coming from, this 0.86, okay? And you would just go through each pipe section using that same process, the appropriate chart, the appropriate columns with pipe size and flow rates, until you ended up with the total friction loss for that entire lateral. So here, let's do another example. Again, note that there are different pipe sizes in the different sections of pipe. Also, the flow rate for each section is shown, and it's different. So what you see here is that the sprinklers are operating, each of them at 4 GPM. So you need 4 GPM here, 8 here, 12 here. As you go back toward the valve, it increases cumulatively. We're also given the information that the sprinklers are spaced 16 feet apart. So what would the dynamic pressure be here? And the idea, again, is to just make sure that you've got the appropriate amount of pressure at that last head to operate all of the sprinklers effectively and efficiently. So here is, again, a table that you can use to organize your calculation. We've got the section of pipe, the type of pipe, the size of the pipe listed, and then, of course, the gallons per minute per section. And the PSI loss per 100 feet, which again comes from the appropriate friction loss chart. So as you would work through this calculation, you'd look at the pressure at the valve, which was 30 PSI. The pressure loss in pipe you will have calculated, and it ends up being 1.51 PSI. Estimated pressure loss in fittings, 10% times that 1.51, or 0.15 PSI, and then you put it all together, ending up with 30 PSI minus 1.51 PSI minus 0.15 PSI for a total of 28.34 PSI at that last sprinkler. Again, going through the use of the chart, if we're considering just section A, the nominal pipe size was 3/4 inch. If you recall, the flow was 4 GPM, so that means the PSI loss per 100 feet is 0.88. But we didn't have 100 feet of pipe, did we? It was 16 in between each of the sprinklers. So for that calculation, you would simply take the 0.88, divide it by 100. You end up with 0.009 PSI loss per foot. You multiply that 0.009 PSI loss per foot times 16 feet and end up with a PSI loss of 0.14 PSI. So backing up here, again, that is where this particular number comes from, and you would go through that process with each of the sections of pipe. So now let's make things somewhat more complex. Here what you've got is a sprinkler system with 2 lateral lines, and there are 3 sprinklers on each lateral. Each of these sprinklers requires flow of 5 GPM. So to run each lateral, a total of 15 GPM is needed at this point in the line. For this example, the sprinklers are spaced 40 feet apart, and section D of the pipe right here, I'm giving you that information, is 50 feet long. Sections C here and E here are 20 feet long. And then you'll just use the same kind of table setup for this as we have in the past 2 examples. So the question is, what is the dynamic pressure at sprinkler number 3? So here we have our table set up. We've got our pipe sections, type of pipe, size of pipe. Let me just back up for a second. Those sizes of pipe are noted here. Okay. Gallons per minute required for each section of pipe, the length that we've got to consider, and then PSI loss from the chart, actual PSI loss by calculation. So there are 60 PSI coming from the valve. The pressure loss in the pipe from the valve to the last head is determined here at 3.93 PSI. The estimated loss in the fittings, pressure loss in the fittings, is going to be 10% times that, so that's 0.39 PSI. And the pressure remaining at sprinkler 3 is going to be 60 PSI minus 3.93 PSI minus 0.39 PSI, or 55.68 PSI. So to sum it up, dynamic pressure is the pressure in the system when sprinklers and emitters are on and functioning. It must be within an acceptable range for efficient operation, so I'd encourage you to Go back and have a look of those typical operating pressures and flow rates for sprinkler and drip components, so you're familiar with what those pressures ought to be. And it's going to depend on pressure at the water source, also friction losses in the pipes and the components, and pressure changes due to elevation. So that's really the end of our basic hydraulics discussion. Hopefully that will help as we go on through the design process. And next we will be talking about pipes and issues with issues and information regarding pipe materials.